Okay, so now, just thank the speaker again. And we'll have our next speaker, D Amoroso from University Bordeaux. And she's going to talk about first principle studies of piezoelectric BCTZ solid solutions.
Good evening, everybody, and thanks to stay until the end. So at first, the reason why we decided to get involved in this theoretical characterization of BCTZ solid solution, because we know that nowadays the community is running for the search of high-performing piezoelectrics without the use of leads. And with respect, already 10 years ago almost, l'URN found a candidate in this barium calcium titanium zirconate solid solution with actually low concentration of calcium and zirconium doping of BTO. And since that time, a lot of experiments actually followed in order to check the phase diagram and the related properties of this material, but actually the underlying physics and the reason why such properties appearing is not that clear. And so we thought that it would be interesting to approach the analysis via step-by-step construction. That means to well characterize the main properties that are arising from the pure compounds. That means from the pure barium titanate, barium zirconate, calcium titanate, pure parent compounds, and the binary system barium calcium titanate and barium titanate zirconate that actually are the building blocks toward the construction of the solid solution BCTZ. And so the big boss here is, as we know, is BTO, that we have seen widely that is characterized by two main factors. The one is that the tolerance factor is bigger than 1. That means that the B site, so the titanium, is small enough to off-center in order to improve the bonds with the oxygen with respect to the ideal cubic perovskite structure. And accordingly, in fact, what we have is that the destabilizing interaction that sustains these instabilities, this distortion, is occurring between the titanium and oxygen atoms. And so, with respect, if you look at the phonon dispersion curves of barium titanate, we have strong polar instabilities that arise from the gamma point that is, in fact, related to the distortion, to the polar motion of the titanium with respect to the oxygen. But what is important to keep in mind from BTO is the fact that these instabilities is chain-like. That means that we need a minimum number of correlated titanium-oxygen chains in order to preserve the ferroelectricity in BTO, because if this condition is not respected, the ferroelectricity in BTO disappears. Then from the condensation of this polar mode, we get an energetics that reflect actually the phase diagram of BTO with a ground state that is represented by the rhomboidal phase. Now, if we look to calcium titanate, that is the second parent compound at play, it shows an identity card that is the opposite, because the tolerance factor is less than 1. So in this case, is the A site, so calcium, that can eventually off-center to improve, to lower the energetics of the system. And in fact, the destabilizing interaction that sustains these instabilities is between calcium and oxygen, and no more between titanium and oxygen atoms. And in fact, if we look at the phonon dispersion curves, what happens is that now we have two major instabilities appearing at the edge of the cubic brilliant zone that are related to the oxygen, oxygen rotations around the titanium atoms. Nevertheless, the cubic calcium titanate still hosts a polar instability that is now restricted to the gamma point. And according to the fact that the destabilizing interaction is between calcium and oxygen, the character of the instabilities is, in fact, dominated by the relative motion of calcium with respect to oxygen atoms. Then, from the condensation of these instabilities, the energetics is quite spread. In fact, what happens is that the antiferrodistortive distortion brings a huge gain of energy to the structure with respect to the cubic phase. However, again, the ferroelectric phases are allowed. They are metastable phases. And it is important to note that the sequence is reversed with respect to BTO, because now is the tetragonal phase that is lower in energy with respect to BTO, where it was the rhomboidal one. And so, now, if we are going to dope BTO with calcium titanate, there are two main mechanisms that will play the major role. One is the fact that we are going to mix two compounds that has two different mechanisms driving the distortion. We have seen that BTO is dominated by the titanium-driven mechanism, while calcium titanate is dominated by the A site, so the calcium site-driven polar distortion. On top of this, we have steric effects, because we know that calcium is bigger than barium, and because of this, we have that finally the volume of calcium titanate is smaller than the volume of barium titanate. And this is reflected in the fact that the titanium-oxygen bond length is contracted in calcium titanate with respect to BTO. So what happens when we are going to face solid solution? Calcium shows the tendency to shorten the surrounding titanium-oxygen bond length. So what happens is that for low calcium concentration, the titanium atoms will experience alternating shorter and longer bonds, while when we are going to higher calcium concentration, the overall size of the solid solution will be reduced, and so all the titanium-oxygen bond lengths will be contracted. And we know, we also proved, that the dynamics of barium titanate is strongly sensitive to this volume contraction. In fact, we see that the kind of interaction between the titanium and oxygen atoms changed to be destabilizing to become stable with the contraction of the titanium bond lengths. And in fact, we have that the polar instabilities disappear with this volume contraction, as well as, accordingly, the energy gain of the polar phases. But on the other hand, we can see that we can consider the fact that calcium titanate will experience an overall increased volume because it's within the matrix of BTO. But this doesn't matter because the interaction between calcium and oxygen stay all the time destabilizing, attractive. And so that means that the calcium-driven mechanism will be a constant in the solid solution. So let's see what is the effect on the energetics of the system. So we have that basically for the low calcium concentration case, the fact that the titanium-oxygen interaction will experience a competition between the attractive and repulsive forces according to the fact that experience alternating shorter and longer bonds, will produce a competition between the A-site-driven and the B-site-driven mechanism, sustaining the polar distortion. And to this competition corresponds a flatness of the energy barrier between various polar states. Then, when we go to higher calcium concentration, actually the overall size of the titanium-oxygen bond length is contracted. So we have that the major mechanism now is the calcium-driven one. And in fact, because we resolved the competition between the two mechanisms, we also resolved, in somehow, the degeneracy, and in fact, the energy landscape became again spread. And what is nice to be noticed is the fact that whatever is the atomic arrangement that we can have, the tetragonal-like polar states is the one that the system prefers, like in pure calcium titanate. But so now let's focus on what happened in this low calcium concentration case. Well, we have that, in fact, this energetics is an anisotropic energy landscape because we have the appearance of different monoclinic phase, and the value of the polarization for all of these states is exactly the same. And to this corresponds a huge enhancement of the piezoelectric response, because, in fact, the system now has the possibility to to experience a different orientation of the polarization without any energy cost. So what we have seen, that when we are going from barium titanate to calcium titanate, we are changing the character of the distortion, the polar distortion. In particular, for low calcium concentration, the two mechanisms, the B site and the A site mechanism, will compete, and this produce a free access to different polar states. And this corresponds to an isotropic landscape for the polarization, and so this favors the enhancement of the piezoelectric response. But now we need also to care about the doping of the B site. And so we need to deal with barium zirconate. Barium zirconate presents a third different behavior because it likes to be cubic, in fact, and accordingly we have that the interaction between zirconium and the oxygen atoms is a stable one. And in fact, zirconium is polar inactive. But so actually we can already imagine what is the effect of this doping. What happens when we are going to substitute one atom of titanium with one atom of zirconium? Is the fact that we are locally breaking the titanium-oxygen correlation chains that is required in BDO to preserve the polarization. But the effect on the energetics is not that obvious, because in fact, as been proved just a few talks before, when we have a low zirconium concentration, because zirconium is bigger than titanium, the overall volume is increased with respect to the one of BTO. And this further favors the stabilization of the rhombohedral phase with respect to BTO. Then, of course, when we go to higher zirconium concentration, the system shows the tendency to prefer to keep an isotropic surrounding. And because of this, it will prefer to keep a kind of rock salt atomic arrangement. But within this arrangement, there are no more possibilities to preserve any titanium-oxygen correlation chain. And so the system will be paraelectric. And so we have seen now that with the doping of barium titanate with barium zirconate, basically the system will progressively lose the ferroelectricity because the zirconium and titanium atoms are strongly related one to each other. But so we got a question. Can this strong correlation change the behavior and make zirconium active? To answer to this question, so we built specific supercells where we preserved the local titanium-oxygen chains by substituting one titanium atoms with one zirconium. And we also took care to distinguish the effect of a decreasing zirconium concentration, like in this super lattice case, to the effectively local effect due to this specific pattern of atomic arrangement. And the answer to the previous question is yes. In this specific, along this specific configuration, so where we have one zirconium followed by several unit cells of barium titanate, actually the system developed a homogeneous polarization all along the chain by making the zirconium atom polar active. And the explanation of this is quite straightforward, because it's the electrostatic coupling that make this activation of zirconium possible and make the... Oh, sorry, what is going on? The electrostatic coupling makes zirconium active. Why? Because otherwise, an eventual mismatch of the polarization between different layers will produce an energy cost from the system. In order to avoid to pay this penalty, the system prefers to develop, to sustain an homogeneous polarization all along the chain. And so we can also interpret this like the fact that we are able to lowering the energy cost to polarize barium zirconate by adding several times the energy gain that we get when we polarize barium titanate. When I say several times, means several times the number of unit cells of BTO that are following barium zirconate. And in this case, it results that already 2 unit cells of barium titanate are enough to develop the homogeneous polarization. So what we have seen, that again, when we are going from barium titanate to barium zirconate, basically, again, we are going to kill the ferroelectricity. And the limit to get a full system that is ferroelectric is around 30% of zirconium. However, if we can imagine that there will be some fluctuation of the concentration within the solid solution by allowing titanium-rich region. In this case, we can preserve a polar nanoregion, not only because of the fact that we have preserved titanium-oxygen dipoles, but now we have demonstrated for the first time that actually this is also possible thanks to zirconium-oxygen-titanium dipoles. But how does this relate to BZTZ? So, well, we have seen that low calcium concentration doping, or BTO, open the access to different polar states without more or less no energy cost. On the other hand, we have seen that low zirconium doping further favors the rhombohedral phase. So when we mix the two now, we are going to simulate a full solid solution with the low calcium and low zirconium concentration. What happened, in fact, is that we got the existence of different monoclinic phase very close in energy. And so the question now is, can be this the reason behind the enhancement of the piezoelectric response in BZTZ? But don't worry, we have done, because I will try to answer to this question in a few months. And so I want just to thank Filippo Gosè and Andres Cano for supervising my PhD, and you for the attention.
Okay, so questions? Well, I guess everyone's probably just trying to get to the dinner. So let's thank the speaker. Oh, there's one more. Please.
Thank you for the talk. I think there is information that barium zirconate, it likes to make antiferrodistortive distortion.
Yeah, that's right.
And let's say, do you reproduce that?
Yes. I didn't show here the phone dispersion cost because it was not related with the polarization properties that we were talking about. But it's true that at the air point of the cubic brilliant zone, there is an antidistortive instability that is quite small, actually. But in fact, some rotation are allowed to lowering the energetics with respect to the cubic phase. But experimentally, from the experimental point of view, people are not still able to observe that structures.
Okay, thanks.
Yeah.
Okay, so let's thank all the speakers in the session.
Yeah, thank you all very much. So I just want to make a quick announcement. So the dinner is at 7:30, which is about now, or a few minutes, and for 1 hour, and then we go for an hour for the poster session, and then we should be leaving the building after that. So please plan your evening accordingly. There will be beer both for dinner and during the poster session. There'll also be beer and snacks. And Peter has an announcement too.
Yeah, just a quick reminder that the talks tomorrow start at 8:30, so you can sleep in an extra half hour. And then I think Jim Scott told me that they're starting a sign-up sheet for anybody who wants to share a taxi to the airport tomorrow. So if you see Michelle by the registration desk first thing tomorrow morning, she can put you on the list.